Hello my friends and business partners from all over the world. Welcome to our channel. My name is Rafael. I'm an electrical engineer, book writer, business English coach, professional translator, and bilingual teacher of mathematics and physics here in Brazil. And on this video, I'm speaking on behalf of RF Consultoria. We are a consulting firm here in Brazil specialized in translating scientific papers and reports from Portuguese to English and in training Brazilian professionals and researchers to rock, to excel in seminars and congresses around the world using the English language, of course. And to demonstrate how to speak about engineering, how to speak about electronics, I brought to you here the circuit containing the LM741, which is a very popular operational amplifier, very popular among electronic engineers. And we are going to learn how to speak about electronics and how to give results about electronics in congresses, seminars, and all sorts of things where you will need to use the English language. Okay? To do that, I brought this exercise. Let me read the exercise. Consider this circuit. Okay, we are going to use the operational amplifier. This is a general representation of operational amplifiers. This is the actual 741, okay? And we are going to use this because this is simpler to understand. This electronic circuit is designed for a nominal closed-loop gain of 10 volts per volt. Why we are using a closed-loop gain? Because if we simply input the signal here in the operational amplifier, the gain will be not stable. Okay, we need to have a feedback loop here to stabilize the gain. And we have defined the gain to be only 10 volts per volt. We don't want 10,000, 1 million, no. We want only 10 volts per volt. This is the gain that we wish. The operational amplifier is specified to have output saturation voltages of positive 13 volts and negative 13 volts, and output current limits of positive 20 milliamperes and negative 20 milliamperes maximum. With this, the questions are: letter A, specify the output for an input of 1 volts peak. I'm gonna have a sine wave of 1 volts peak at the input, and we want to specify the output for this input. Letter B, if the input has a peak of 1.5 volts, then specify the output. Letter C, I want the maximum value of the output voltage, the maximum value of the peak of the output voltage for a load resistance of 1 kilo ohms. And letter D, I want the lowest value of the load resistor if the input is 1 volt. The peak of the input signal is 1 volt. Okay, now that we know everything, we know what's being talked about, I want to calculate what's been asked. I'm going to erase it here, okay? And let's solve it. Let's talk about it. Let's train discussing it, okay? Because you will need to know English to present your result in a seminar, okay, in a conference. Then let's rehearse it. Okay. We know that the gain is 10 volts per volt. My input is gonna be like this, okay? Okay, 1 volt times the cosine Wt plus phi volt. I'm not interested in the frequency, and the phase is not important. What is important for us here at the moment is only the peak of the sinusoid. If the gain is 10 volts per volt, then the output voltage will be, of course, 10 times the input voltage. Alright? Very simple. Very simple. Okay, now the other thing that we need to calculate for letter A is the current. Okay, the current, we are going to have 3 currents here. We're going to have 3 currents here. And I want you to pay attention to understand the difference between the 3 currents. I'm going to have a current here. That is the current that leaves the device. The current that goes to the load is going to be this current here. And there is another current that goes to the feedback loop. So, I0 of t, which is the current that leaves the device, we will have IF, which is the current of the feedback loop, and IL, which is the current that goes to the load. We can calculate this and then come up with this. Okay, IF of t is going to be equal to the voltage, this voltage here, that is from this output terminal to ground, which is the same here. Okay, same here, from here to ground here. Okay, we know that R2 is 9 kilo ohms, and we know that R1 is 1 kilo ohms. 9 plus 1 is 10. Then it's going to be equal to 10 times the cosine Wt plus phi divided by 10 kilo ohms. Okay? 10 divided by 10 is 1. Then we know that IF is 1 times the cosine Wt plus phi amperes. This we know. Okay. I'm going to write it here. 1 cosine Wt plus phi. And now we want to calculate the current that goes to the load. The current that goes to the load. The current that goes to the load is equal to the voltage, the output voltage, 10 times the cosine Wt plus phi divided by 1 kilo ohms. And then this is 10 times the cosine. Oh, sorry, this is in milliamperes. Sorry, I made a mistake. 10 times the cosine Wt plus phi milliamperes, alright? Milliamperes. Then I'm gonna write here 10 times the cosine Wt plus phi milliamperes. It's in milliamperes. Okay. If I make a mistake here, please correct me. Okay? Nobody's perfect. I make mistakes. And for letter A, I0 of t is going to be 1 plus 10, 11. 11 times the cosine of Wt plus phi. Alright, milliamperes. Milliamperes because the load resistance is 1 kilo ohms, and these resistances here are also in kilo ohms. Then the output current is going to be 11 times the cosine Wt plus phi milliamperes. Okay, and the limitation that the exercise gave us was that it should have been under 20 milliamperes. 11 is under 20 milliamperes, so we are operating in the normal band, in the normal range of the device. Okay, and just to illustrate what's gonna happen, just to illustrate here for letter A, just to illustrate, we are going to have an input signal of the sort. And here, this is Vi, this is T, and here at the output, we are going to have a signal that is amplified, okay? So this is V0. This is the input, this is the output. The input signal is 1 volts, and the amplified version, the output is the amplified version, is 10 volts peak, okay? Do you guys fully comprehend what's going on here? Alright, let's move on to letter B then. On letter B, we want the input signal. We are going to test the device. We are going to see if it holds, okay, if the values provided in the data sheet hold. Okay, we want the input signal to be equal to 1.5 times the cosine Wt plus phi volts. Okay. In the data sheet of the device, it's written that it's going to saturate at plus minus 13 volts. Then the gain will not be 10 volts per volt. We are going to saturate here, so the output voltage will be equal to 13 cosine Wt plus phi volts. Okay? What's gonna happen? A phenomenon will happen here, which is clipping. There is going to be clipping of the output voltage. Okay? There will be something of the sort. We are going to have here the input voltage and here the output voltage. The output voltage is supposed to be like this. However, as we are exceeding the saturation values of the device, clipping will happen. Clipping. What is clipping? Clipping is this here. Clipping is this. Because the device is going to saturate. The device is going to saturate at positive 13 volts and negative 13 volts. There will be clipping of the output voltage. Okay, now that we know this, we are going to calculate the currents that will flow in the device. Okay, out of the device, this current here, I0 of t, will be IF of t plus IL of t. However, V0 of t is not going to be 15. It's going to be 13 because it's the maximum value that the amplifier can amplify. It's going to saturate at 13. Okay? Are you guys understanding? Then, let's calculate this current first. The current of the feedback loop. IF is going to be equal to 13 times the cosine Wt plus phi divided by 9 plus 110, 10 kilo ohms. And this is going to be 1.3 cosine Wt plus phi milliamperes. Milliamperes. Okay? I am going to write it here. So we will not forget 1.3 times the cosine Wt plus phi milliamperes. Now we are going to calculate the current that flows here. It is going to be IL, the current of the load is going to be 13 times the cosine Wt plus phi volts divided by 1 kilo ohms. The resistance of the load is 1 kilo ohms. And then this is equal to 13 times the cosine Wt plus phi milliamperes. Okay, we are almost finishing. Hold on, be patient, we are almost finishing. Okay, then 1.3 plus 13 gives us the current of 14.3 times the cosine Wt plus phi milliamperes. This is going to be the output current. And it is under the limit. We know that the limits are 20 milliamperes. 14 is under this level. So we are not going to exceed the capability of the device. Alright, let's move on to letter C. Okay? Letter C asks us what? The maximum value of Vp for undisturbed. We don't want to disturb the output. Okay, the exercise asks us, if RL is 1 kilo ohms, what is max VIP? The maximum value of VIP, of course, will be the limit. The maximum value of is going to be equal to 13. Okay, so Vi of t needs to be maximum 1.3 times the cosine Wt plus phi volts. Because when we amplify, it will become this 13, 10 times this cosine Wt plus phi volts. Okay, and as we know, we calculated for letter B the value of the current, the value of the output current is going to be 14.3 times the cosine Wt plus phi milliamperes. Alright, so this is the specification of the output. We want the maximum value of IP for the load of 1 kilo ohms. If it's going to saturate at plus minus 13 volts, then the maximum value of the input voltage has to be 1.3. When we amplify, it becomes 13. And the current that comes out of the device, this current here, is 14.3 times the cosine Wt plus phi. Alright, to finish, let's go to letter D. Letter D asks us about the lowest value, isn't it? Do you remember? Let me check. What is the lowest value of RL? Lowest value of RL. The lowest value of RL for undisturbed outputs, but we want this for VI, P equal to 1 volt. Okay. Remember, the maximum current, the maximum output current is plus minus 20 milliamperes. Okay? Alright? We are going to use this value here. Beyond this, we are going to have disturbed outputs. This is the limit for undisturbed outputs. Then, the lowest value of the output resistance needs to be equal to 1 volt divided by 20 milliamperes. Alright? And is that it? Is that it? Is it right? Am I being right? Okay, let me use my calculator here. It is gonna be 10 divided by 20, which is 0.5. So it is 500 ohms. 500 ohms. This is the lowest value of the load resistor. This is the lowest value of the load resistor. My friends, this was the video that I wanted to make. I hope you guys enjoyed it. I hope you guys learned something from it. Okay? This is how you speak about electronics. This is how you use the English language to speak about electronics. This may be very easy for you as an engineer with experience, because you have worked with this for 10 or 20 years, but when we have to speak another language, this can be hard. Then I made this video on behalf of RF Consultoria to prepare people to talk about their scientific discoveries to the world using the English language. I'm going to leave our number on the description of the video. If you have any interest or doubts, you can contact us and we are going to respond to you. So this was the video, my friends. Goodbye!